Today's lesson we're going to look at doing integrals of logs and exponents. So we did derivatives of logs and exponents in a previous unit. So today we're going to do the reverse and figure out how to do. So if you remember back from derivatives, the derivative of e to the x stayed the same. And then we just had to remember if we had a different exponent, so if we had something like e to the 3x, the derivative stayed the same, and then we had to multiply it by the derivative of the exponent, so we had to times it by 3. And it doesn't matter what the exponent was. If you had e to the x squared, we would keep it the same, and then we would times it by 2x. So that's how we did derivatives. So now we're going to be doing the integrals. So because the derivative of e to the x stayed the same, the integral of e to the x also stays the same. And then we put the plus c on just because it could have a constant as well. The other type of exponent that we did was when it was a different base. So if we had something like 3 to the x, oops, my pen's not working. But if we had something like 3 to the x, remember we then kept it the same, except we would have to times it by the ln of that base. So I won't bother writing, my pen doesn't seem to be working on this page, but you can see the idea. If a to the u, we keep it the same, but then we multiply it by the ln of that base. We can see here when we have integrals now, we just got to remember to do the same process. So if it's an e, we keep it the same. And if it was a derivative, we would times it by -3, but since it's an integral, we need to divide it by -3, or we could times it by 1/3, whichever makes more sense to you. And that's it. So exponents, keep them the same, divide by the derivative of your exponent. Here's another one. So this one has base 4, so remember we'd keep it the same, and derivative of the exponent is just 1, so we divide by 1. But now, because it's base 4, we'd have to times it by ln 4 if it was a derivative, so we're going to have to divide it by ln 4. So you can see the ln 4 on the top, and we do the reverse, we divide it by ln 4. Those are going to end up canceling out. So our final answer should just be 4 to the x plus c. And remember, we could always do the derivative backwards to see if it works in case you weren't sure. So before we move on, let's just try one more here. If I gave you just 4 to the x without the ln 4. So now we would keep it the same. We would divide by the ln 4, and we would have to divide by 1. So we could leave it like that, or we could write it as 4 to the x over ln 4 plus c. So you can see it works pretty much the same, just whether the ln 4 there is not. What's nice about the ln 4 is it kind of reminds you that you need it when it's not a base e. So let's just try a couple other ones here. So what would it be if I gave you something like integral of x times e to the 3x squared? Okay, so even though it looks like it's a product rule, we got things being multiplied. We don't have to worry about that x because it should cancel out. So if we worry about the exponent, keep the e the same, and then we would divide by the exponent, which is 6x. So you can see the x's end up canceling out, and our final answer would just be 1/6 e to the 3x squared. Okay, so just like it was with chain rule, if you have an x out front, it needs to cancel, otherwise this method isn't going to work. We're going to have to come up with a different strategy later on. So let's try another one. How about if I gave you 3 ln 2 times 2 to the 6x. So the 3 ln 2 is just a coefficient. Let's just leave that alone. 2 to the 6x would stay the same. Now we'd have to divide by 6. And because it's base 2, we would divide by ln 2. So you can see pretty much all of that stuff cancels except the 3/6 would turn to 1/2. So our final answer would be 1/2 times 2 to the 6x. And we could even be a little fancier if we want. We could write that 1/2 as 2 to the -1. And we can use exponent rules to combine them with the same basis. So we'd add exponents. So we could even write it like that. It would be fine if you didn't. If you left it as just the 1/2 would be okay, but in this case, because they're both base 2, we can combine them into a simpler form. Okay, so that takes care of exponents. So now the next thing is, how do we do logs? So if you remember back when we did a question like 1 over x squared, right, we could do that question as a power rule. We would just make it x to the -2, and then as a power rule, we would raise the power by 1, divide by that new power, and we'd be done. So if it was a positive, like 1 over x squared, it worked fine. If we had just a regular positive exponent, right, obviously those ones worked fine because we just raise the power and divide by the new power. And even if we did something like just x to the 1, right, we don't need the power in there, but we could treat it like x to the 1. So we'd raise the power, divide by 2. So that one works pretty good. Or even if we had just a number like 1, right, that would be like x to the 0. Even that one we could raise the power and divide by 1, which would do nothing, so that would just be x plus c. So all of those work good as a power rule except for 1 over x. Because if we write that as x to the -1, and if we follow the same power rule steps, we would raise the power to 0 and divide by 0. Can't divide by 0. So this is the only one that doesn't follow the power rule. So if you remember back to earlier units when we were doing logs, that was the derivative of ln x. So when we had y equals ln x, the derivative became 1 over x. So then if we had something like ln of 3x minus 2, our derivative was 1 over 3x minus 2, and then we times it by 3. We times it by whatever the derivative was. So that's what the du dx is, just times it by the derivative of whatever's inside the brackets. And then when we had a value that wasn't ln, so we had something like log base 4 of 6x minus 2, that derivative we went 1 over, and then we divided by the ln of the base number. So in this case, we could just write it as ln 4 times 6x minus 2 on the bottom, and that would be totally fine. So that's how we dealt with logs. Derivatives, so now integrals obviously would be the reverse. So what we're going to be looking for is these scenarios where we have 1 over something. So 1 over x becomes ln x. In the formula you can see we have absolute values. That's just there to indicate that we can't have a negative log. So it's just restricting the domain so that it'll always be positive, so that the log or the natural log would work. So don't worry about it too much, just write it with absolute value brackets instead of regular brackets. Okay, so let's look at a few examples. So here you can see it looks like a quotient rule question, and that's probably the hardest part with this, is sometimes they're hard to identify what strategy to pick. But we can't do quotient rule yet, we don't know how that works. If we tried to write this as a chain rule, it would look like that, but then again we'd be raising the power to 0 and dividing by 0. So that doesn't work. So the best thing is when you see something on the bottom to the power of 1, if you wrote brackets around and put it to the power 1, that should give you a hint that we got to do it as a natural log. So our 3 would stay the same. We would do natural log of x plus 2, and then we'd have to divide by the derivative of the x plus 2, which is just 1, so that doesn't do anything in this case, and that would be it. So we'd have 3 ln x plus 2. And that's it for that one. Okay, so here's another one. You can see the bottom part would be, think of it like brackets to the 1. We have an x on the top, but that won't matter because it should end up canceling out, or more importantly, it has to end up canceling out. So let's keep the x the same. We have natural log of whatever's on the bottom. And our derivative of the brackets would be 2x, so we need to divide by that 2x. So we can simplify that to just 1/2 ln x squared plus 5 plus c. Again, we can do whether it's open intervals like this, or if I gave you some values, if I said we're going to go from x of 1 to 2 or something like that, 1 to 3, we could then calculate an actual decimal answer. So plug in the 3, subtract the value of 1, and that would be your final answer. So it works the same whether they're open intervals or definite integrals. Okay, here's the last one. So again, you can see it's something to the power of 1 on the bottom, but we can actually see there's a ln 3 already. So that, remember, is going to tell us that we're going to change it to log base 3. So we should be able to do the same sort of strategy. Leave the 2x alone. That ln base 3 will change it to log base 3, and we'd have our bottom value, so the x squared minus 1, and then we would divide by the derivative of the inside, which is 2x. So in this case, the 2x cancels. That ln 3, we don't have to worry about it. You could leave it on there, but then we'd be doing the reverse, we'd be multiplying it by ln 3, which would cancel out. So we can do that. Let me just show you that in case you like it better. So we leave the ln 3 on the bottom, but then when we do the integral, normally if it's log base 3, we times it by, or we divide it by log base 3. In this case, we're going to have to multiply to do the opposite. So those would end up canceling as well. So you can skip that step if you want, it doesn't really matter. So our final answer for this one should be log base 3 of x squared minus 1 plus c. And that's it. That's basically it for integrals. We could also combine these with trig. Let me just do a couple quick examples. So if I gave you something like e to the sine x times cos x, right? We just follow the exponent rule part, so keep your trig the same. And then we'd have to divide by the derivative of the exponent, which is cos x. So those would end up canceling out. So e to the sine x plus c would be our final answer. So whether it's trig, whether it's logs, whether it's power rule, you can follow those same basic rules. So I think that's enough examples. We'll stop there, and that's it. We'll move on to quotient rule and product rule type integrals in the next topic.